to start by acknowledging also the co-authors of this work, Ling-Seng Meng, Han Bao, and the rest of the UCLA team, and also Eric Fielding, Curran Lian, and Chris Milliner at Caltech JPL, who also contributed with the remote sensing analysis of this work. Also in the acknowledgements for the funding that we have received both from the French institutions, Université Côte d'Azur, here in the south of France, NSF, postdoc fellowships by NASA, and also acknowledge the data that has been made available by different institutions, including IRIS, and without convenient and free access to the seismological data, for example, we wouldn't be able today to do the analysis that I will show you, and actually to do it in a timely manner very quickly after each large earthquake. I will also like to acknowledge interactions that seismologists I've been having with my colleagues on social media, and it's a wonderful thing that I discovered a couple of years ago that many of us are on Twitter, and there's a lot of brainstorming going on there after each large earthquake. So if you haven't, please join the GeoTwip world on Twitter. I've had only fantastic experiences with that. And also wanted to thank all the previous theoretical and methods development work that has been done and published by previous authors, which we have benefited from, especially work by Yihe Wang, especially during her PhD with me, by Martin Vallée from IPGP Paris, by Eric Dunham from Stanford, and Harshabad from École Normale in Paris. Here's the overview. I'll start with a very brief background on the Palu earthquake, and then we'll jump onto the observations, both kinds of observations, satellite, static observations, and seismological dynamic observations of what happened during this earthquake, and what are the key unusual and interesting features of this earthquake. And after showing you the observations, we'll talk a little bit about the dynamic models of fast supershear ruptures to understand a bit why this was so surprising, and also to try to interpret some of the most unexpected features of the earthquake, and finally closing with some of the implications and of these observations. Most of the results that I will show today have been published very recently in Nature Geosciences. And for those who don't have access to the journal, you can access the preprint on Earth Archive, which is a 1 year old, a little bit more than 1 year old archive for the geosciences. So these are preprints that are available for free for everyone, before even the publication of the paper. So let me start with the background on the Palu earthquake. Here on the left, we see an overview of the tectonics of the area. In the inset, if you can follow my red cursor here, we can see a much larger view of all the tectonics of Southeast Asia, Indonesia. Palu is in the Sulawesi island, so let's focus on Sulawesi. There's a subduction zone in the north. There are subductions also to the south and to the west, and there is this long strike slip fault that accommodates a lot of the deformation, and that runs across the island of Sulawesi. Let's move to the figure on the right, where we see more clearly the trace of this fault. The bay that you see here in the north, this very narrow bay, is the Palu Bay. The city of Palu is at the southern end of this bay, and you can see that the fault runs just across the urban area and on the side of the bay. So the earthquake started somewhere here in the north, about 100 kilometers north from the city of Palu. And as we will see, it propagated to the south along 150 kilometers rupture. This fault was not unknown to the local people and to everyone. It's a fault that has been studied by geodesy, for example. We knew that it was a fast-moving fault and it was accumulating energy and it was capable of large earthquakes, and a fault that had produced large earthquakes in the past. So if you look at the hazard map of Indonesia, over a very broad scale here, the Palu Koro fault is in red, so it's a well-known, very hazardous area of Indonesia. Nevertheless, there were surprises from this earthquake, and you probably have seen all this and other impressive images of the damage caused by the shaking, but also by the large high tsunami that happened due to this earthquake. The surprise came from the fact that this is a strike-slip fault, and strike-slip faults are not usually the first culprits of large tsunamis, basically because these faults don't have a lot of vertical motion on the seafloor, and that doesn't cause a lot of high tsunamis. So there has been a lot of discussion about what was the real cause of the tsunami. Was it some vertical motion on the fault? Was it some horizontal offset of very steep slopes of the seafloor? Or was it the triggering of submarine landslides that then triggered the tsunami? Or was it a combination of all these possibilities? On the right, we see some examples of also the very widespread landslide, liquefaction, and lateral spreading secondary effects of the earthquake. Massive damage due to this phenomenon in the city. Here again, one of the big questions is, was any characteristic of the earthquake actually aggravating these secondary effects? So let's now move into the key observations that we have gathered in our study. And I will split it into three. The first is the remote sensing observations done by satellites, and these are mostly the static observations. And then we'll see two ways of assessing the dynamic parts of the earthquake, one by teleseismic back projection, and the second technique by identifying evidence for a surface wave Mach cone. Remote sensing, what we see here on the left is the result of analyzing synthetic aperture radar images by satellites. So we have to wait and take a snapshot of the Earth before the earthquake and wait that the satellite goes through the region again, take a second snapshot. And from the differences between those images, one can infer the relative displacement between before and after the earthquake. This particular satellite, its track is shown by this black arrow here. And you can see that the path of the satellite was almost parallel to the fault. The fault trace is drawn here in black and the thin black line. So the sea is here in gray and the land is covered by these red and blue colors, which are the satellite results. All right, what the colors show are basically the displacement along the track of the satellite. Red means displacement to the north, blue displacement to the south. And where you see the contrast between red and blue, that's where you expect the fault to be. That's where the offset is accumulated. So a couple of interesting observations out of this analysis. This star here is the hypocenter, and we can see the displacement, of course, only inland, not on the bay and not north from here. We can see that this offset is present down to a rupture distance of about 150 kilometers. So that's a rupture length inferred from the satellite image. And if we look at the offset across the fault, that's the slip, and it reaches very high values, of the order of 6 meters in the city of Palu. Another interesting feature is that the fault is not straight, and there are 2 visible large bends on the fault, one here in the northern part of the rupture, and another bend here in the southern part of the rupture. This will become important in a minute. Besides radar imaging, one can do also optical images from satellite, and these are some examples of analysis of optical images. This allows you to get a little bit better resolution on the displacements across the fault. The color scheme is similar to the previous one, but here we have now 2 components of displacement imaged by the optical technique. And if we make a cross-section across the fault over these images, we can make profiles of displacement across the fault. So 0 here is when we cross the fault, and you can see this step here in displacement, and the offset accumulated in this step is the slip. You can do this over different cross sections along the rupture, except of course in the Palu Bay. And the result is plotted here on the right. So this is basically a profile of a slip along the Palu Coro fault. One interesting point is that the slip was much higher in the southern half of the rupture than in the northern half of the rupture, again reaching a slip on the order of 6 meters in the city of Palu, but maybe only around 2 meters in the northern part. So that was static information, the difference between before and after with images that are separated by several days or more. We want to also have a look at what happened during the earthquake on the short time scales of the duration of the earthquake rupture, which is less than a minute. One way to do this is by teleseismic back projection. So let me first explain in simple words what is the principle behind this. It's an analogy is how our ears work together with our brain to locate and track sources of sound around us. How does that work? If there's a sound source, the sound will reach first one of your ears, and then a little later the farthest ear. There's a tiny time delay of sound wave arrival to your 2 ears, and your brain makes use of that tiny time difference to figure out where the source is located. And if the source moves, you can track the motion of the source. So we're going to do the same with seismic waves, but we are going to need a very high resolution, and to improve the resolution or the accuracy of this processing, we're not going to use bigger ears. What we're going to do is we are going to use hundreds of ears. And our hundreds of ears as seismologists are big arrays like the US array, which is shown here in this slide. So thanks to these major investments and efforts and initiatives to deploy super large and dense arrays, we can do the sort of processing that I'll show today, back projection. Here are examples. These are very beautiful products made by Iris. Each time there's a sufficiently large earthquake, we can see in colors here how the ground motion moves across the US array. And there's two examples here. On the left is an earthquake in Samoa Islands, and on the right, an earthquake in Japan. And what you can already see from the pattern of the waves is that you can tell that where the waves are coming from. So this pattern, the move out of the waves across the array, are the information that we will use to locate the earthquake and also to track the propagation of the earthquake. These couple of movies are also very useful for you to appreciate that if the array is not dense enough, so let's look at the western side, the eastern side of the US here, where the separation is very coarse between the stations. It's basically impossible to figure out what is the pattern of these waves, and you lose this ability to locate and track the source if your network or your array is too coarse. So this is the interest of having dense arrays. Now, something that you may not notice on the movie in the right is that the direction of arrival of the waves is not constant. It's changing slightly. This is explained in this sketch on the left. So imagine that the red star here is the hypocenter, and this is an earthquake that propagates along, let's say, 100 or 200 kilometers. The waves that are coming from the hypocenter will reach the array with a certain angle of arrival, and the waves coming from the endpoint of the fault will arrive with a different angle of arrival. So this will generate different patterns of wave travel times through the array. And they're subtle, so we need to use what we call high-resolution array processing techniques to identify these differences and use them to track the propagation of the rupture along the fault. Once we have identified the move out, so the pattern of waves on the array, we can convert that into origin time and location of the source on the fault. So this is the back projection part of the processing. And in this way, we map each of these waves onto a time and location on the fault. And with this, we can make movies like the one on the right. So in each frame of this movie, the warmest colors indicate the most likely point of wave radiation on the fault. This example on the right is the example from the Tohoku earthquake in 2011. Now, this technique has been around for more than a decade. This was introduced for large earthquakes right after the 2004 Sumatra earthquake by people like Miyake Ishii and Peter Shearer. And it is a type of array processing. It's something that is very present in everyday life, actually. If your cell phone and cell phone towers are using this sort of processing all the time to try to locate where your cell phone is relative to all the cell phone towers and then optimize the telecommunication. There are some challenges that are very particular to seismology. One of them is that the crust or the earth is very heterogeneous, so there's a lot of scattering. There's also a lot of attenuation in the earth, so we wish we could use very high frequencies to do this, because the higher the frequency and the higher the resolution that you can get, but scattering and attenuation pose a limitation on how high we can go on frequency. There's not much we can do against that. Another challenge is that the sources of seismic waves are moving very fast. In this context, fast means that the earthquake rupture is moving at a speed that is comparable to the speed of the seismic waves, which are the information carrier. So this is very different from the cell phone problem. You don't walk as fast as the electromagnetic waves that are being used to locate you. So we had to develop some more advanced techniques in, actually this was mainly the PhD thesis of Ling Meng to deal with this aspect, fast moving sources. The other challenge is that we very often have multiple sources active at the same time. A rupture front can be very big and it can radiate from different spots simultaneously. So that's also something that we had to take care of. And some more technical aspects of the technique, so-called swimming artifact, which is also something that we had to fix during Ling Meng's thesis. More recently, there has been more developments and by various teams. Actually, this technique has been in steady advance, but something that we found very useful, and this is a slowness-enhanced technique that was introduced by Ling Meng a couple of years ago. And the principle here is that we can use aftershocks or foreshocks, smaller earthquakes in the same region, to come up with semi-empirical corrections that will improve the accuracy of the spatial location of the back projection sources. The figure on the left shows you in the blue stars are the epicenters of several aftershocks of the Palu earthquake. And the red stars are how the initial back projection locates them. So you can see that there's a big difference between the blue star, each blue star and red star pair. All that is inaccuracy introduced in the back projection technique. And this is because there are some simplifying assumptions, of course, when we do back projection. So here the idea is to come up with a correction for the slowness of waves that can be applied to the whole region. And it is going to be a slowness correction, so it's a physics-based correction that will minimize the uncertainty or the error in the back projection location of the aftershocks. So in this way, the slowness correction is computed, and then we can apply that to the back projection of the main shock. So this, for this particular example, has reduced the location error from something on the order of 25 kilometers to something much narrower, like 7 kilometers. Which data did we use for this analysis? We considered many different arrays that were at teleseismic distances, so between 30 and 90 degrees to Palu. We considered those that had data that was conveniently available. You can see that we didn't use the Chinese network for this early study. The resolution of the array processing also depends on the aperture of the array, which is the size of the array. So the bigger the array, the more resolution you can get. The closer the array also, the more resolution you get. And then the azimuth also matters. There are some azimuths at which the ratio between the direct P wave and the depth phases is comparable, so that makes the back projection a little bit more complicated. So we have to avoid some azimuths that are not optimal. It turns out that the Australia network gives the highest resolution results for this earthquake. It is a large array and it's close enough to the Palu earthquake. When we repeat the analysis with the New Zealand array, which is at a similar azimuth, so we find consistent results, but of course lower resolution because the aperture of the array is in the radial direction. It's not as large as the aperture of the Australia array. So I'll show in the following only results from the Australia network. Here's the main result in this animation on the left. Each colored circle plotted here on the left is the location every 1 second of the most likely spot of coherent high frequency radiation. And when I say high frequency, I mean frequencies between 1 and 2 hertz. We filter the data in that frequency band to do this analysis. So one thing that is confirmed, you can see by comparison to the background, which is in red and blue colors, which is the satellite image, is the whole propagation length, which is about 150 kilometers. If we didn't do the slowness correction, actually there would be a large significant bias on the rupture length. And if you have a bias on the rupture length, you also have a bias on the rupture speed, which we'll see is a very important feature of this earthquake. So the earthquake propagated to the south, at least a high frequency of part of the earthquake propagated to the south. This figure on the right shows you the vertical axis, the location of these sources along the strike, and the horizontal axis is the timing of these sources. And at the end of the movie, I drew a line here that goes through the leading front of this high frequency radiators. That leading front is interpreted as the leading rupture front, and the slope of this gives you the rupture speed. It turns out that is on the order of 4 kilometers per second. This is definitely a rupture speed that is faster than the S waves in this area. So it is what we call a supershear earthquake, an earthquake that breaks the fault faster than S waves. Another interesting feature is that this speed seems to be quite steady along the rupture, despite that the fact that the fault has these 2 big bends. So that is surprising, because you can think that it's like driving a car on a highway. Of course, if you go through very steep curves, you're going to have to slow down. So maybe the same intuition would work for earthquakes, and this would be a counterexample of that, that despite these large bends, the rupture didn't seem to care and just kept cruising across at a very fast speed. Let me move to the second type of seismological analysis that we did to confirm actually that the speed was high. So how does this analysis go? If you have a source that is moving faster than S waves, it will produce what we call a Mach cone. Maybe the most simple or most common analogy for this is the sonic boom of a supersonic jet plane. You can see this cone that is being generated by the jet when it goes past, with its speed exceeds the speed of acoustic waves in air. So in solids, this also happens, and there are these beautiful experiments by Aris Rosaki's group, where they produce in the laboratory earthquakes, and some of them run at supershear speeds. And when they do, with optical measurements and really, really high-speed cameras, they can image the deformation outside their laboratory fault, and they can see this cone here of deformation that is analogous to the sonic boom cone. We are going to deal with surface waves, because the Mach cone of the surface wave is predicted to be persistent to very large distances. And unfortunately for the Palu earthquake, we didn't have any strong motion instrument very close to the fault to see a Mach cone of body waves. And I think a better analogy for the Mach cone of a surface wave would be the wake of a boat that is traveling faster than the speed of water waves. And this is a better analogy because surface waves are dispersive, and water waves, short wavelength of water waves, are also dispersive. So you can see here this conical shape, but you can also see all these other wiggles here inside at the edge of the cone that are the effect of dispersion. And if you want to learn more about this, actually these things have been figured out only recently. I was surprised by that. There's some interesting physics papers about ship wakes. So why does the Mach cone have this particular features? And we can try to understand this for these sketches here that come from Eric Dunham's website on Supershear earthquakes. She's one of the researchers who have worked on Supershear and on the fundamentals of Supershear the most recently. Actually, the Supershear earthquakes were first predicted theoretically back in the early 70s. And it took a long time for seismologists to convince themselves that this could really happen in the Earth. Two examples here. On the left would be the fault is this thin gray line here, and then let's think of an earthquake that's propagating along the fault. At the time of the snapshot, the earthquake is somewhere here, and these circles are the wave fronts that have been radiated by the earthquake as it moves. In the Supershear case, there's a pileup of waves here, and this is the Mach cone. So first, it produces this conical shape if you were to take a snapshot of the formation of ground motion. And also because these waves tend to pile up on the Mach cone, their amplitude, if the waves are coherent, tends to be very high. So this is very similar to just the basic directivity effect for those of you who are familiar with that. If you are if you have a station that is situated along the fault, and that station is, and the rupture is propagating towards the right, for example, in this figure, and your station is to the left, you are going to see a longer apparent source time function, because the apparent duration that you see to the left is not only the real duration of the earthquake, but also the difference in time of the travel time from the two tips of the rupture. So in the anti-directive portions, we tend to see longer rise times. In the regions that are aligned with the rupture, we tend to see much shorter rise times. And this is for a subshear earthquake. For a supershear earthquakes, we see this shorter rupture durations, not along the rupture, but along the cone of the Mach cone. So once the rupture stops, all these waves that were on the Mach cone continue to travel along this paths here. And if you turn out to have a station that is located along the path of the Mach cone, it will see a very short apparent source duration. So now if you compare the seismograms from a small earthquake to the seismograms of the main shock, the large earthquake, if you are not on the Mach cone, you're going to see a relatively large source time function, and the main shock waveform will be pretty different than the small earthquake waveform, just because it is convolved by the longer source time function. But if you are on the Mach cone, basically the main shock waveform is equal to the small earthquake waveform convolved by a very short source time function, which is basically a delta function. So these two waveforms, small earthquake and main shock, along the Mach cone will tend to be very similar. This was a method that was introduced actually by Martin Vallée and Eric Dunham back in 2012, and this was applied to the Kunlun earthquake, which was one of the very large supershear earthquakes observed in the past decade. And in our paper, we just took this method and applied it to the Palu earthquake. And you'll see that there's a lot of data to do this. There are all these stations along the Indonesian arc, and there are all these stations in Australia. And the prediction is that if we compare the waveform from a small earthquake to the waveform from the main shock, on stations that are inside these bands here, which are the edges of the cone, the Mach cone, the waveforms should be very similar. And there's two examples here, the two top seismograms. You can see that they are extremely similar. And if we do the same comparison, but for stations that are outside the cone, you predict that the similarity will drop down, and that's exactly what we see. These seem very different waveforms when you are outside the Mach cone. Different in phase, different in amplitude too. So this is a confirmation that the Palu earthquake was super shear, and actually we can even confirm through this analysis that the super shear speed was sustained along most of the rupture. All right, so in summary, the observations that we have here are a rupture speed close to 4 kilometers per second, super shear. It's a fast speed. Something that I didn't emphasize before is that it starts fast from very early on. And the third point here is that the speed was pretty steady and sustained despite the large bends that we see on the rupture trace. Why are these features interesting? So let's put this in the context of dynamic models of super shear rupture, but also in the context of previous earthquakes. Now, super shear earthquakes are pretty rare. So there's only, let's say, a handful of super shear earthquakes that have been observed, maybe a good dozen of them. Some of them are summarized in this figure from one of my papers with Yihe Wang. The horizontal axis here is the rupture speed normalized by the shear wave speed, S wave speed. Magnitude is on the vertical axis. All of these symbols here on the top part of the figure are estimates of rupture speed from past earthquakes. You can see this, in some cases we've been able to also plot their uncertainties, their error bars, if you want, when they were available. And you can see that estimating rupture speed is actually tricky. The uncertainty on estimates of rupture speed are very large within a method, and actually for some of these earthquakes we have estimates from different teams and different papers, and you can see that there's some large disparities between them. All right, the colors in this figure are important too. There are some speeds that are physically forbidden. There's no earthquake that can propagate for long distances and sustained at speeds faster than P wave speed. P wave is the fastest speed of seismic waves. So ruptures cannot travel faster than that. Most earthquakes travel at speeds that are slower than the S wave and slower than the Rayleigh wave speed. Very typically, average rupture speeds are on the order of 70 to 80% of the S wave speed. Rayleigh wave speeds are typically 90% of the S wave speed. So most large earthquakes are below Rayleigh. So we call them sub-shear or sub-Rayleigh speeds. There is a range of speeds between the Rayleigh wave and the shear wave speed that is forbidden, in the sense that an earthquake cannot, in homogeneous medium, cannot travel at a sustained, stable speed that is between Rayleigh and S-wave speeds. There's another interesting speed here, which is the Eshelby speed, which is a square root of 2 times the S-wave. So that's about 40% faster than S-wave. And in most dynamic models, theoretical and dynamic simulations, Eshelby speed separates 2 different regimes. One that we call this stable supershear, and the lower one that is called we call the unstable supershear. And what this means is that ruptures can propagate at these speeds in the gray band here, the unstable supershear. But if a rupture is traveling at this speed, a very small perturbation will push it to either faster speed or slower speed. So that means that this speed is unstable, in the sense that it's really hard in a simulation to sustain in a stable way this range of speeds. The most common speed that is obtained for supershear earthquakes in simulations is actually close to the P wave speed, somewhere here. So there are some earthquakes for which the speed has been inferred to be, at least by some people, to be in this gray area here. You can see that the error bars are pretty large. The Palu earthquake is one that also falls in this unstable supershear speed range. So it is a supershear earthquake. It's a fast one, but it's not as fast as we would expect. It's not as fast as a P wave. What do we see in laboratory experiments? Most of the laboratory experiments also show speeds that are in the stable supershear range. What do we see in numerical models? Most of those numerical models tend to accelerate and run at speeds that are as fast as the P wave speed. There are some numerical models that we did with Yihewang that actually can cover other speeds that are unusual, and I'm going to show you what was so special in those numerical models now. But before I do this, there was one idea proposed by Michel Bouchon and co-authors. By looking at previous supershear earthquakes, their observation was that the supershear portions of past earthquakes were coincident with parts of a fault that were very straight and had very simple geometry. This is what makes it surprising that the Palu earthquake was supershear from very early on, and despite these big bends on the fault. So it's a counterexample of some notion that was emerging in recent years. All right, so why the dynamic rupture models that we ran with Yihewang in her thesis produced these unusual speeds? We accounted for the fact that faults are not surrounded by intact rock, but they are surrounded by damaged rock. And this is something that you see in the field. You see it also from geophysical methods, that mature faults are surrounded by several hundred meters thick areas where there's a lot of secondary fractures, microfractures that reduce the wave speed within the damage layer. And if we account for those low velocity zones around a fault in our dynamic rupture simulations, we find the following features. These two movies here are ground motion outside a fault. The fault in both cases is running at the bottom of the figure, and this is just part of velocity outside the fault. The bottom example has a low velocity damage zone, and the top example is just a homogeneous medium without a damage zone. And the big difference is that when you account for a damage zone, there's a lot of energy that remains trapped within the low velocity zone. These are reflected waves and trapped waves that then come back to the rupture and interact with the rupture and can boost the rupture. And what we have seen in this simulations is that by this effect of the low velocity zone tends to enhance the stresses, the dynamic stresses on the fault, and this turns to facilitate the supershear transition. So it's easier to get supershear earthquakes in these models when we account for the low velocity damage zone. What's interesting is that in these simulations, the supershear earthquakes also tend to accelerate to the P wave, but not to the P wave speed of the intact rock. They accelerate to the P wave speed of the damaged rock, which is slower. So if we put this in the context of the Palu earthquake, it would be sufficient for the Palu coral fault to be surrounded by a few hundred meters zone that has a low velocity, 30% lower velocity than the intact surrounding crust. And this would be sufficient to explain the observed rupture speed, meaning that the 4 km/s observed speed could be the P wave speed inside the damage zone of the Palu coral fault. Some implications of all these observations and discussion. First, as you can imagine from the analogy with the sonic boom and this shock wave here, is that if you are on the path of this shock wave, the amplitude of the ground shaking will be much larger. And this is actually what Eric Dunham and Harshabad have explored in their paper in 2008. These are examples of the peak ground motion outside a fault in 3 different cases. The top one is for a subshear earthquake, the bottom one is for a fast supershear earthquake, and the intermediate one is a supershear earthquake, but not that fast. And as you move to increasing speeds from top to bottom, you can see this intensity of the ground shaking to become larger and larger, so as expected intuitively. Faster the rupture, the stronger the shaking, and thus the stronger the expected damage. And this actually brings us to some speculations. So it is possible that it's an interesting question to ask. How did the fast rupture of the Palu earthquake actually influenced the secondary effects of this earthquake? What if the stronger shaking produced by this fast rupture actually was the trigger of more or larger submarine landslides? And what if these submarine landslides in the end also aggravated the tsunami that was observed? So these are interesting questions that that we are researching, and also I am aware that other teams are also looking at this question from the standpoint of dynamic rupture. It would be really nice to get additional observations, but as I said before, there's no strong motion data available that recorded this earthquake close to the fault, so we'll have to rely on other types of observations, and this will take more time to be collected. In summary, so let me end here. Our observations made thanks to seismological and remote sensing analysis is that the earthquake was a supershear earthquake. It propagated faster than S-wave speed. This rupture speed was sustained steadily despite major fault bends along the path. And the supershear speed was a bit slower than expected. One interpretation that we can propose is related to effects of a damage zone. So one of the open questions is, of course, is there a damage zone around the Palu coral fault? And this is something that can be determined by doing seismic experiments close to the fault in the future, or maybe some people are already jumping at that opportunity. And of course, the big question is, did the fact that the earthquake was super shear, that was fast, did that affect in any way the cascade of secondary effects that were observed, from shaking to submarine landslides to the tsunami? And thank you for your attention, and I'm open for your questions.
Great, thank you, Pablo. So we have quite a few questions that have been written in already, but if you have a question, please make sure that you type it into the question box that's available on your GoToWebinar control panel. So a first question, I think it's related to one of your introductory slides, is from Anna Skorkina. She asks, why are some bends and kinks associated with high values of displacement and other bends are not?
Mm-hmm. So I don't know if we see really that sort of correlation, but if you've seen it, one possibility is that it's actually the orientation of the fault bends. This is a left lateral fault, so and you can see that the angle made by these bends is different, the one in the south and the one in the north. So one of these bends is a restraining bend and the other one is a releasing bend. The restraining bend will tend to increase the normal stress. Slip will tend to increase the normal stress on that type of bend, and that will strengthen the fault, and that can reduce the slip. And conversely, on the releasing bend, the normal stress on the fault will go down with slip, and that can facilitate actually slip and further rupture.
Great, thank you. Baptiste Gombert asks, what are the off-fault HF radiators? Are they real or are they artifacts? Thanks.
Let me bring you a figure. We can see it here. Yes, there's a lot of scatter in the cross-fault direction, and I don't think all of this is real. So there's a difficulty in doing this more accurately than is shown, is that there's a lot of wave scattering in the Earth, and then there's an effect of unknown 3D velocity structures that contribute to the uncertainty of these high frequency locations. So we have to be careful not to over-interpret the images that we see here.
Okay, great. Alex Hutko asks, did other arrays show support for super shear, even though they may not have been as ideal as Australia? And like, for example, using the data from China?
I haven't seen the back projection with the data from China. That we'll have to ask Ling-Seng Meng if he has done that. What I remember is that when we tried it with the New Zealand array, overall it confirmed the super shear speed. But of course, the image wasn't as sharp as with Australia.
Great. Christelle Wattier, sorry if I mispronounced everyone's names, but says, nice talk. Is there a significant non-double couple component, excuse me, visible on the moment tensors? And as a follow-up question, how did you combine Sentinel-2 and Planet Lab measurements to estimate your offsets?
Okay, I can answer the first question, which is in my domain of expertise. From my recollection, I don't have a figure here of the focal mechanism. And non-double couple component was not substantial. I don't remember it being very large. You expect a little bit of non-double couple in this case because the fault is not straight, but I actually don't remember it was anything large. For the Planet Labs imaging, which is the work of Chris Milliner, I'll have to defer to Chris Milliner for the details of the technique. But it's all described. It's basically cross correlation between the optical images. So you take a few patches of pixels and you find the optimal spatial shift between those patches of pixels between the picture before and the picture after the earthquake, and that's the way you compute these offsets.
Great. Yunjin Zhang asks, is there evidence of the bend at depth in the tomography data that may explain the steady rupture speed?
You mean a bend at depth?
There was no additional explanation in the question. Sorry. Okay. Take your best stab at it.
All right. So something that is interesting is that an interesting question that I found by looking at this is it's possible that these bends, we're seeing these bends at the surface, right? And one way to reconcile this with the idea that was proposed by Michel Bouchon, that these earthquakes, the supershear earthquakes, tend to happen only on very straight faults. It's possible that these bends do not exist at depth. And if that is the case, so most of the rupture is actually maybe going through a smoother and more straight fault at depth than what we see here at the surface.
Yeah, and the question was like the bend, does it show, tomography show a bend or no bend? And so I think that's like an updated to the question. So is the bend just a surface feature? I guess.
I haven't seen it finer enough tomography and tell us that.
Okay, great. Walter Mooney asks, the HF sources are all east of the surface fault trace. Is this a location error or does this imply a dipping fault?
I think this is mostly location error.
Indra Gunawan asks, what is the information that can be attained if there was a strong motion record close to the epicenter?
Oh yes. You could see the Mach cone of the body wave. And you could also address that question, whether the fact that the earthquake was supershear amplified the shaking.
Marino Pernotti asks, hello, hola Pablo, have you plotted rupture velocity versus stress drop to see if what we might intuitively think that high stress drop produces faster velocity ruptures, new faults are faster? Is that correct?
So overall, one way to address that is by looking at the magnitude versus the rupture length of the earthquake. And this 150 kilometers length is not unusual for earthquakes of this size. So stress drop average is not unusual. A second order information is from the optical imaging, especially from this sleep profile. The fact that the sleep is 3 to 4 times smaller in the northern part might be telling us that the stress drop was 3 to 4 times smaller. Or maybe the rupture depth or the seismic depth was smaller. It's a trade-off between these things. But despite these differences, the rupture speed was equally fast in the north and in the south.
Interesting. Ignacio Sepulveda asks, what do you think about the fault trace beneath the bay? Is there any argument to rule out a stepover or an additional bend?
We don't have any argument to rule out with the data we have, or the data I've shown here. I think I will have to wait for maybe differential bathymetry, or I think even if you look at the current bathymetry, there's some morphology that you can see there that has been interpreted by some as evidence that there's a geometrical feature there.
Okay. Tabrez Ali asks, would an existence of a hypothesized damage zone near the fault also dampen high frequency, like 3 hertz ground motion? And will it be exacerbated by the sediments draining from the mountains near Palu?
The sediments, I don't think will make a big difference because they are superficial. This effect will low velocity damage will have to persist. A big part of the seismogenic, which means probably down to 5-7 kilometers deep. I forgot the first part of this question.
I will send it to you. And
sorry.
No, it's okay because I'm kind of deleting them as they go along. So, but I will send it to you. I'll make sure that everyone's questions get answered. So Hector Gonzalez Huizar asks, nice presentation. Are supershear rupture velocities characteristic only of strike slip faulting, or have they been observed under other tectonic environments like subduction zones? In other words, what could be the role of large-scale tectonics in the rupture speed?
In theory, this has to do with the relative direction of slip compared to the direction of rupture propagation. They have to be parallel for supershear to happen. On subduction earthquakes, the slip is mostly vertical, whereas rupture propagation is mostly horizontal. So they are orthogonal, so we don't expect supershear to happen in those situations. Nevertheless, there's very deep earthquakes for which there's been at least one observation of supershear earthquake, and this one was propagating upwards.
Yeah, interesting. John Dale Dianella asks, could the location of the HF radiators, especially those further away from the fault, be an indication of a damage zone?
I think we should be careful not to interpret the fact that there's an offset between the fault and the radiators, or a significant scatter lateral of the radiators.
Good point. So Esteban Chavez says, first off, greetings from Costa Rica. And can we characterize or assume that the Palu earthquake is a runaway earthquake?
Okay, so my definition of a runaway earthquake is an earthquake that if it had available an infinite fault, it would just continue to run and nothing will stop it. Now, this is a definition in the ideal world of computer simulation. I'm not sure exactly what you are thinking of, or how you're defining runaway earthquake. But the interesting question is what stopped this earthquake here? Why didn't continue? There is actually the fault continues. So that's an important question.
I see 2 more questions, and then I think we'll wrap up because I know it's getting very late on your end. Navid Kirdask asks, is there any kinematic inversion available from this rupture process?
Yes, there are. Some that were made quickly in the earthquake, some that were even fed into tsunami models very early on. I haven't done one, but I know that several teams that are having.
Okay. Oh, Tabraz Ali wrote in with the first part of the question, which said, would the existence of the hypothesized damage zones near the fault dampen high frequency ground motion along 3 hertz?
Very good question. Yes, a damage zone has low velocity, but it also tends to have strong attenuation. It's also a place where a lot of dissipation can happen due to inelastic deformation. So yes, you're right. That's one of the things that we're testing on our current dynamic rupture model. You should also look at what Alice Gabriel is doing in Munich. They've done some dynamic simulations of this earthquake, and also follow what Harsha.
Okay, Felipe Vera asks, and I think this will be our last question. Hi, Pablo. Why does the high frequency radiation track southeast movements and not a clear pattern along the fault zone revealed by the remote sensing observation? Is it an effect of the array location or something really expected?
Yes, there is uncertainty, and part of the uncertainty is due to the azimuth from which we are imaging the rupture. So Australia is to the southeast, and that makes larger error in this direction.
Okay, so thank you, Pablo, for answering that really engaging Q&A session, as well as giving such an amazing presentation, especially given the time zone that you're in. And so I will make sure there's just a couple additional, I think, smaller questions that I will send all of your questions to Pablo and make sure that he has all of your information to follow up in any way that he sees fit. And I want to thank you again, Pablo, for giving this presentation today. And thank you all for attending. We had 80 attendees live, so that's a great turnout. And again, this will be posted on our IRIS YouTube channel. And, please feel free to go back and rewatch Pablo's really engaging presentation. So thank you, everyone, and I hope you have a great rest of your day or evening. So get some sleep, Pablo. Thanks so
Thank you, everyone.
All right, take care, everyone. Bye.
Bye.